to start momentum and impulse. The good news is our new-ish equations are derived from old equations. So the concepts of what we'll be talking about are not new, even though it may look new, okay? And it all starts with Newton's second law. And so someone remind me, so we're on the top of page 1, taking some notes. What is Newton's second law? What kind of force equals MA? What kind of force equals MA? Net force. And so net force equals MA. So this is where it all begins. We're just going to kind of play some games. We're going to sub in and rearrange. Who remembers the defining equation for acceleration? Perfect. Change in velocity over change in time. Okay. It's not average velocity over time. It's change in. To accelerate means we speed up, right? But it's even more than just speed. I know that we've spent a month saying, oh, scalar, scalar, scalar. Energy is scalar. It only cares about speed. Y'all, now we're going back to vectors, okay? Acceleration is a vector. And I don't know if I pointed it out in the fall, but look at the formula chart close to you. Find Newton's second law. Do we see these little arrows on top of the force and acceleration? Do you know what those arrows indicate? Vector quantity. And so force is a vector. Change in velocity is a vector. Okay. And so overall, we got to put back on that vector hat just in a second. Okay. Direction matters. Okay. So what we're doing today is back to vectors. Direction matters. Okay. And we're not done with energy, by the way. Energy is the cousin of momentum. You'll see. Sorry, my microphone is shutting itself off. Okay, well, let's do a little rearranging and get this in impulse and momentum fashion. And so what if we multiply both sides by change in time? We'll get net force times time equals m delta v. And we can keep those vector symbols here. Are y'all okay in the back? Okay. If you need to separate, that could be advised. Okay. Okay. So this is the equation that I'm going to highlight because this is impulse and change in momentum. Now, it may not look like it, so I'm going to keep it going. This is equal to impulse. Now, impulse does have a variable. AP took it off their formula chart. I don't know why, but the variable is a J. So joules, it can get a little confusing, but if you see in the packet or as you read review books or you read your textbook, videos, whatever, capital J in an equation is impulse, okay? And so what is impulse? Well, yeah, it's a force times time equal to a mass times change in velocity. But here comes our other new equation. Little p equals mv. What is little p? Well, this is momentum. And you're like, okay, that doesn't make sense. I've heard, I keep forgetting to Google it, but something like the Latin term, the parent word of it meant progress. So that's what I tell myself. And so to have momentum, notice what it takes. You need mass and velocity. Well, gee, what energy depends on mass and velocity? What energy? Kinetic, okay? And so momentum and kinetic energy are very directly related. They're not equal numerically. They're not equal by their equation, But if you have kinetic energy, half mass times v squared, you have momentum, the product, mass times velocity, which if somebody exerts a force on you, can't your velocity change? Yeah, push something. And so momentum, by the way, is mainly the examples you'll see are crashes, are bounces, are throws, are hits. So hitting a baseball. We've done those problems before as projectile, where we care about it going through the air. We looked at the split second it left the pitcher's hand or left the bat. Now we're looking at the time that the bat hits the ball, the time that the pitcher throws the ball, okay? Time is important. And so just note to self that this time that the force exerts. So it's during the throw, it's during the hit, it's during the kick. If you kick a ball, right? Does this make sense? So impulse is change in momentum. Impulse isn't momentum. That delta is very, very important. And so take a look at your formula chart. Hopefully it's close by. Notice what they give you and what they don't. They do give you the base equation for momentum, but then they just tell you a change in momentum is Ft. But true story, you're going to have to use the m delta v version of it, okay? And so this is more of a working equation. Let's look at units. What would be the unit for momentum? This is outside of a number. And so mass times velocity. What's our unit for mass? Kilogram times the unit for velocity, which is meters per second. Nothing cancels, nothing squares, and it doesn't simplify. There's your unit for momentum, kilogram, meter per second. Don't say kilogram per meter per second, kilogram, meter per second. Well, if it's equal to a force times time, you could also state your unit as a Newton times second, a Newton second. Okay, similar to what we had with Newton meter, a Newton second is the unit equivalent to kilogram times meter per second. Okay, here's my norm. If I use force and time to get an answer, I use Newton second. If I use mass and velocity, I use kilogram meter per second. You don't, either one, they're equal. Okay. Okay, so there's impulse. And again, this is kicking, throwing, hitting, crashing, anything that exerts a force during a certain amount of time. It can change the momentum of another object, yes? Okay. Graphs that we may see with momentum, well, velocity is still involved, so you could still have velocity time graphs, but your new one, newish, in work, we saw a force times position graph. Here we have a force versus time graph. Now let's not make it too easy on ourselves. We could have a constant force. That could be easy enough. But what if we have not a constant force? How could we get momentum information? Well, force times time gives you change in momentum. What graphical strategy do we want to do to get force times time? Area. And so area will give us a change in momentum or impulse. It's the same thing. Change in momentum and impulse, same thing. And so notice with a triangle, you got that 1/2 base times height because your force is not constant. And so this is really going to be like an average force times time. So if you do the 1/2 base times height, it takes care of that average piece for you. Slope wouldn't really be anything. It would be the rate at which your force is changing. We don't really have a name for that. And then you can read it, right? So you could get a max force off of it. You could read at what time did, you know, whatever. But area would be the common thing to do with a force time graph. All right, now to conservation of linear momentum. So linear momentum, y'all don't know any different, but after spring break, when we do rotation, we'll see angular momentum. It's going to be similar but different. And so here we have conservation of linear momentum. Well, this is just an extension of Newton's third law. What is Newton's third law? Equal and opposite reaction. So the way I'm not going to write it out, I'm just going to symbolize it. If I have one ball or whatever, one car, hit another object, the force on one is equal to the force on the second object, right? So the bat hits the ball. They exert a force on each other. Newton's third law says those are equal forces. Well, what if I multiply both sides by that time elapsed? And so I know it looks like I'm adding 2, but if you multiply the left side, you got to multiply by the right side, and we keep our equality, yes? So the delta t in both of these is the same on both sides. Remember, it's the time of the hit, the time of the kick, the time of the throw. And so from here, this is an impulse. So you could look at Newton's third law as equal and opposite impulse. It's kind of a new way, equal and opposite impulses during a collision or during the interaction, whatever it is. And now we can plug in, well, impulse, force times time. Actually, before we take the equation further, what kind of relationship does force and time have? I should have asked this up above, but either way, I heard it. Inverse. So side note here, F and T have an inverse relationship. So what does that mean? For this thing to be equal, maybe I have a large force and a small time. That can equal a small force and a large time. And you're like, what's the big deal? Y'all know what airbags are, right? We want airbags in our vehicles, right? Why? It does increase the time. So if you're in a car wreck, not that I ever want anyone in a car wreck, but if you're in a car wreck, that airbag deploys, right? And gives you a cushion. Cushions soften the blow. They give us less force. And so your airbag hurts less than hitting the dashboard or hitting the steering wheel without an airbag, right? And so anything with a cushion, okay, whether you're jumping out of a burning building into the, net or whatever the fire department has brought, anything that increases the time to bring you to a stop is that inverse relationship. It's better than hitting the concrete below, right? Jump into the net, not the concrete below. Yes.
If you're jumping into below the falling into an airbag, then is it like a spring quality of the? Yeah,
the cushion quality of it decreases the force on you, but for it to be equal, it has to increase the time that it takes you to stop. And so y'all, in a car crash, no one's timing, right? That's what the labs do, the engineers do ahead of time. But if you compare airbag to no airbag, the dashboard and the airbag both bring you to stop. They will both change your momentum to 0, yes? But the dashboard is going to hurt a lot more, right? Cause more injury. And so anything that has that cushion aspect is because of this inverse relationship with force and time, okay? Anything with it. So go back to sports. You're catching a line drive, right? Baseball. you're catching. Do you want to catch it barehanded? That high-speed baseball? I'll stop it. Assume I do catch it, I'll stop it. But ow, right? Gloves have that padding. And also, when you catch something, do you just hold your arm out like this? Straight in front of you, catch, end of story? What do? You let it come back. Our body, our joints have built-in cushions, right? And so letting the ball go as you catch it like this, or if you're jumping off a high table, or I'm not going to try it, but you bend your knees when you jump off, right? Gymnasts, when they dismount one of the apparatus, they always bend their knees and then come up. What's the bending knees? If you don't bend your knees, that's a lot of force on your joints. Break the bones, okay? So, I mean, it's never ending examples, okay? So anything that bends to cushion or is a literal cushion is implementing that change in momentum. Good deal? Okay, let's keep our equation going. So F times T, well, that is impulse. That is change in momentum. And so here we can sub in change in momentum for both sides. And y'all, there's a lot of subscripts. A lot of subscripts. Let them be your friend. And so this is saying that during whatever crash or interaction, two balls colliding, the change in momentum of one ball is equal and opposite to the change in momentum of the other ball. Now, careful, am I saying the change in velocities? No, maybe they're the same mass, maybe they're not, okay? And so now let's break it down into the mass piece. So I'd have m1 times change in velocity 1 equals, keep that negative, it's part of Newton's third law, m2 times the change in velocity of 2. And again, if you want to put the arrows, velocity is still a vector, whether you put the arrow or not, right? Well, now that's delta V. Delta tells us to do what? Final minus initial. So in each one, I'm going to say final velocity of 1 minus initial velocity of 1 equals a negative m2, and then final velocity of 2 minus initial velocity of 2. Now, sometimes your examples, maybe they both have the same initial velocity, maybe they both have the same final, but worst case scenario, all these numbers will be different. And so having those subscripts can help keep it straight. And then before I move my initials and finals to a single side, what if we distribute that negative to both velocities? And so the right side, and I know I'm bleeding over into the types of collisions, it's okay. It's okay. We would have a negative m2 vf2, and then negative, negative, I have a positive m2 vi2. On the left side, it would be m1 vf1 minus m1 vi1. And one side has a negative on each. So what if we add them to the other sides? And so I'll add the negatives to the other sides to make them positive. And so here's our next to last line. M1 VF1 plus M2 VF2 equals M1 VI1 plus M2 VI2. Now, so far, I've just been focusing on two objects. But does that mean that every single collision or crash or interaction is just two objects? No, okay? You could have, if this is a literal car crash, which by the way, some of our examples are car crashes, okay? It's an application of momentum and impulse. No one gets hurt in physics land, of course. But you could have multiple cars in the crash, right? In fact, this time frame, Last year, wasn't there like 30 car pileup on that icy week that we had? Okay. I don't remember I-30, I-20, somewhere in there. It was horrible. It was horrible. Moral of the story, this equation only has two. I'm going to dot, dot, dot on both sides. What if it's three objects colliding? Well, you're going to put them in there. They wouldn't really show up in that original statement, but look at what's happening. The momentum final of both objects adds together. The initials add together. And so this is that conservation of linear momentum. It's the momentum that your system begins with equals the momentum that you end with. Of course, here comes the asterisk, here comes the clarifier. As long as there are no external forces on the system. And so all that system approach that we took with energy, it's still here, okay? Is the system your object? Is it object Earth? Is it the objects plural, right? And so that stuff still isn't going away. But if you say there's no external forces that do impulse on the system, then within your system, linear momentum has to be conserved, okay? Most of the problems you'll see will have a conservation of linear momentum, okay? I would say, 10, 20%, just making it up, are going to have maybe friction, right? Which is going to take away momentum even without the crash. Everybody good? Okay, so where did conservation come from? Well, it came from our impulse, Newton's third law, right? Equal and opposite force. And so just like with energy, conservation of energy happened because of the work energy theorem. Now we have impulse leading to conservation of momentum. So it's kind of similar in that regard. Just don't forget, momentum is a vector. Momentum is a vector. Okay, let's get a table drawn of our types of collisions, okay? And so hopefully you have room, squeeze in a table. I'm going to put it in table format, and it's going to be 5 rows and 5 columns, but not all equal in size. So the top row is just going to be for labeling. First column will be for labeling. The second column needs to be pretty big for big writers like myself. This is going to be the description, kind of what to look for. And then the last 2 columns will decide what's true about the momentum for the system and the kinetic energy. Again, they're cousins. And then the first header will be the type of collision. Now, at the end of the day, when you're sitting at the May 12th AP Physics exam, there's only 2 types of collisions, period, just 2. But we're going to break one of those types down into 3 subcategories, okay? And so, 4 total. But note that the last 3 are all going to have a connecting factor. This will make more sense once we finish the table. All right. So the big 2 types of collisions are elastic, but we're not talking springs, we're not talking rubber bands. This is kind of a different designation. It's about the elasticity of your collision. And then in that offshoot box, I'm going to say inelastic. So at the end of the day, on the AP exam, the difference is not whether they stick together or bounce off like a common website might spit out. So if you just Google this and get, a basic understanding of collisions, it's not the AP designation. So I'm going to fill out that last column. The last column is what makes an elastic or inelastic collision. Elastic collisions conserve kinetic energy. And I'm going to highlight that. Okay? If on the AP, if on our problems, you see the word elastic, boom, it means kinetic energy is conserved. Okay? If it's considered inelastic, it means that kinetic energy is not conserved. Not conserved. Not conserved. Okay? And so what is an elastic collision that would conserve kinetic energy? And by the way, I'm going to put conserved on all the momentum ones with an asterisk down below about net external force equaling 0. So that goes back to earlier when I said momentum was conserved as long as there's no net external force on the system. So all collisions, again, no net external force, have momentum conserved. But some of the collisions look different than others. And so what is elastic? So a couple of things, kind of going to use bullets here. And so for elastic collisions, there is a bounce off. There's a bounce off. So a ball bounces on a floor. Is it elastic? Well, let's go to the next criteria. Are there any energy losses? And it's not just kinetic energy. So what we're not saying does it slow down. We're saying is some of that kinetic energy converted to heat? That's really the one that we focus on. You could convert some of it to sound energy, which we don't study, to light energy, which we don't study. But we study work done by friction. That's your heat, okay? And so, hold on. I miswrote. We don't have any energy losses. Apologies. Benefit of OneNote. So I'm going to say no energy losses. Like heat. And we can add in also, look at your objects, there's no deformation. No deformation. So if we think about car wrecks on an everyday basis, unfortunately, when there's a car wreck, don't the cars deform? Yeah. And so that deformation, although it's built in as a safety feature a lot of times, right? You'd rather the bumper buckle rather than you buckling. I meant like wrecking buckling, not the seatbelt. You should always wear your seatbelt. Seatbelt saved my life during a wreck one time. So would have had a broken neck had I not been wearing that seatbelt. Wear your seatbelt. But anyway, your elastic collision, your best example of this, and maybe I put this in a 5th type column, an example would be something called a Newton's cradle. Who knows what a Newton's cradle is? What is it?
Well, there's these 4 balls that are like swinging and they have like elastic. I mean, there it is.
There it is, right here. And so here's a Newton's cradle, and no, I'm not going to pass it around because every time I do that, they come back tangled or tore off, and they're not easy to fix. So if you want your own Newton's cradle, it's a pretty popular thing. Amazon, everybody online has them, right? And so Newton's cradle, what is this? These are hard steel marbles, right? Circles. So they're not made of clay, because clay deforms easily, right? So you want something that doesn't deform. And they're not squares because when they hit, you have low heat loss Low contact when they're circles. Imagine if these were all squares, blocks. When they hit, that would be more surface area touching, right? And so you'd have more heat loss. And so these are the best example, as well as billiards. If you know pool billiards, those, they're not marbles. Those balls are not steel, but they're very hard material. And so after one collision, they really don't deform. Now, yes, they flake off or they can get chipped, depending on droppage type, but overall, those keep their shape during a collision. Good deal? And there's tricks we can play with here later. Let's finish our table. Okay, so that is a elastic collision. If the problem says elastic, boom, kinetic energy conserved. That's what should go through your head. So what about inelastic? Why divvy it up into 3 different categories there? And so at the end of the day, if you Google search for inelastic, in the 3rd row, I'm going to put completely inelastic. This is the common way to define inelastic. And so what happens? They stick together. No bounce. They stick together. So 2 cars collide and stick together. Well, this one has a lot of energy losses. Okay, and we're talking heat, deformation. Okay, this one has a lot. That's your typical inelastic, but we call it completely inelastic or perfectly inelastic, because there's a difference between completely and partially. So partially inelastic is honestly the most challenging one, because the objects still bounce. So it gives you the feeling of elastic, and hold on, one note just quit working. Hold on. Okay, at least it was a quick fix. And so in partially inelastic, there is a bounce off still, but it's not going to be like the hard steel. So this is like a basketball or tennis ball hitting the wall or hitting the floor. There's some deformation with that, right? If you've never seen a slow motion video of a tennis ball hitting the racket, I'll share it with y'all through Canvas or something, but it deforms, right? It doesn't keep its shape. And so we have some energy losses and deformation. Some. Good on that. And then what's the third inelastic? This one is kind of, it could be a category on its own, and AP doesn't really designate this one. It's just what we see. So I'm going to do the description first. So this one is different because they start together and end apart. Maybe you've ridden a skateboard and you jumped off, right? You start together with the skateboard and you jump off. Or right now, I'm standing in front of this podium. Could I push on the podium and move it one direction? Force, what does my body do? We studied this with Newton's third law. If I push the cart forward, the cart pushes me back. If I was on skates, I'd roll back, right? Or we take this to the ice rink. And so they start together, they end apart. It's not really a collision. It's not really, I mean, we've already got partially, here we go, you ready? It's a anti-collision. And these are not official terms, by the way. It's an anti-collision, or it's like the completely inelastic, but in reverse, or go extreme. It's like an explosion, right? Now, explosions have some chemistry involved as well, but your basic explosion in here would be jumping off that skateboard, okay? Explosion in the loosest sense. So whatever you call it, and again, it doesn't really have an official name, but they start together, they end apart. Kinetic energy is still not conserved because your explosion, or here with my podium, you could all start from rest, have no kinetic energy. And then it has kinetic energy at the end, okay? So it's not always about losing. This one would be a gain in kinetic energy, but it's definitely not conserved. Good deal? Okay. And so kind of got the examples in for that one. You're partially or completely, you know, I think car crashes can go in either one, right? Stick together or not stick together, either way. Questions on page 1 notes? Okay, I feel like I'm missing something. Hold on one sec. Where's my table there? No, that's it, that's it, that's it. I did that. Inverse relationship, we talked about vector. We talked about J. I think we got it. Okay, so let's do a quick example. Page 2. Page 2. At the top, and these are your basic level 1, okay? These are not AP, it's just to get us going and thinking about what to do with impulse and momentum. It says the following were applied to the same object. One object, one mass, constant mass, which provided a greater change in P. And I know that's capital, but that's meant to be a lowercase. It's a change in momentum, AKA impulse. Rank the following scenarios. So we've got a 4 Newton force for 1 second. So what's your change in momentum? 4 Newton seconds. B, 2 Newtons for 3 seconds. That would be a change in momentum of 6. Well, come on, one note. Now it won't write. There we go. 6 Newton seconds. What about if we push something with 1 Newton for 2 seconds and then instantaneously push 2 Newtons for 1 second? What do we do there? We add them. So it would be the impulse of 1 and then the impulse of the second. And so we'd get 2 Newton seconds plus 2 Newton seconds for a total of 4 Newton seconds. So your final ranking would be B is greater than A equals C. Okay. Don't average the 1 and 2 Newtons for 1.5 or anything like that. They are individually happening. Not too bad. What about the next question, number 2? A 50 kilogram object, what did they just give us? Mass is initially at rest, or maybe scenario B, it's moving to the right at 10 meters per second, or scenario C, moving to the left at 10 meters per second. So they just gave us 3 different initial scenarios. So if you want to think of it as 3 separate objects, you can just make sure they're all the same mass. And so A has an initial velocity of 0. I don't know why I said 1. And then B has an initial velocity. I don't know, today, do y'all feel like right is positive or negative? Because remember, direction matters now. Positive. So we'll say B has a positive 10, and then C, initial velocity, negative 10. And so now they say a force of positive 20. Now, really, A and B aren't going to give us issue, but let's refresh our memories about motion here. If I've got an object moving to the left, but it's getting pushed or pulled to the right, what's it going to start out doing? It's got to slow down, right? Eventually come to a stop before it can change direction. And so here we know a force of positive 20 newtons is applied for 2 seconds. Rank the following: delta P. Well, I don't know my final velocities. I don't know my final momentum. But remember, delta P, impulse, is that force times time. And so everybody got a 20 Newton force for 2 seconds. Everybody gets the same 40 Newton second impulse. The impulse is the change. It's not what you were. It's not what you'll end with. It's the change. Okay? And now that we know the change, how can we solve for the final momentum? What do those two parallel lines mean? Absolute value of your final answer. It doesn't mean ignore direction completely, just from your final answer. And so let's take a look at A. So delta P equals final minus initial momentum. And for object A, it started at rest. What's its initial momentum? 0. So this zeroes out. And so your final momentum would be that 40 Newton seconds. What about object B? Change in momentum, final minus initial. Now we have a change of 40. We're looking for the final. What's the initial momentum? Careful, they did not give us the momentum. They gave us the velocity. And so momentum is mass times velocity. So I got to say 50 kilograms times that positive 10 meters per second. So 50 times 10, 500. And then we got to add it to the other side to solve for final momentum, which would be what? A positive 540 Newton seconds. And then the last one, what about object C? Change in momentum equals final minus initial. So 40, they all had the same change. We're solving for the final momentum. Minus, well, we have that same MV we need to do. And so 50 is the mass. This one was moving to the left, 10 meters per second. And so on the right side, negative times negative 500, that becomes a positive 500, but I got to subtract it to the other side. And so I know they said ignore, but if we didn't, we'd have a final momentum of negative 460. Now when we go to do our ranking, we'll rank ignoring that sign. And so we would get what? B is greater than C and then A. Make sense? Okay. So we'll pick up here next time. And as far as I know, Wednesday, no ice on the road, at least in the daytime, right? I think the scare is it's going to be raining on Wednesday and through the night, and temperatures dropping 30 degrees. So sleet. Just if you're driving, please be careful. Sometimes physics hurts. Okay, it's real.